most of what we're going to talk about next happens in the small intestine. And so I'm going to draw you, our whole goal is to take the stuff, we just broke down our glucose we broke down our carbohydrates into essentially glucose molecules, and now they're hanging out in the lumen of the digestive tract. That's just the inner space of the tube. Now, as we know, I'm going to draw just a single cell in my small intestine. This is a small intestine cell. Here's its nucleus. And we know that there's a whole bunch of them. And in fact, I can't help it. I have to draw you what it actually looks like, even though I'm not drawing it on this cell because I need to have some space. But do you agree that my actual cell in the small intestine is going to have this crazy high surface area? What are these things? What are those little surface area twangers? Dog pounds. Those are microvilli. And the microvilli do nothing more than increase surface area. So what I'm going to draw you in my small intestine cell, I'm going to show you the transporters that are going to help us absorb carbohydrates from the lumen. So we're talking about carbs here. And what the heck? Let's just talk about glucose. If we talk about glucose, that's going to make it easier. What is that? Go away. Goodbye. It's a polka dotted glucose. Guess what? There's nothing that I'm about to tell you that you don't already know. In fact, you could probably build the cell that would absorb glucose. Where's it absorbing it to? Don't forget, our whole goal is to get stuff into the blood. So the whole purpose is to absorb glucose from the lumen of the digestive tract through the epithelial cell, which is the small intestine cell, and through the interstitial fluid and into the bloodstream. That's our whole goal, because glucose, dog pounds. That's awesome. That's like golden money. We better get that into our cells and get them there quick. Real fast. Where's our bloodstream going? Where's it? Where does the blood take the glucose? Indeed, it is so. We're headed to the liver. We're headed to the liver through the hepatic portal system, which is one of my favorite anatomical structures in the body. We're going to send all of that stuff to be filled. Everything that gets reabsorbed, everything that gets absorbed from the lumen of the small intestine is going to get sent to the liver just to make sure that it's safe. Okay, who do you think might be involved in this whole process? Well, I've got exciting news for you. One guy that's involved, somebody you know, and I'm drawing, it's a transporter. It's SIGALT. Do you guys remember SIGALT? SIGALT, sodium glucose transporter. SIGALT operates by taking glucose against a concentration gradient by moving sodium down a concentration gradient. So sodium is coming into the cell through SIGALT, down its concentration gradient. If you want a sodium concentration gradient, what are you going to have to do? You're going to have to pump sodium out of the cell. Who's this? Yes, indeed, that's your sodium-potassium pump. The sodium-potassium pump, sweetness, is going to send sodium out, creating a concentration gradient inside of this cell, which motivates sodium ions from the lumen to hitch a ride through SIGALT. When a sodium ion hitches a ride, glucose, when sodium says, thanks for the trip into the cell down my concentration gradient, that's easy. Glucose says, I'm going to come along on this little adventure. And so glucose also gets a ride in. Once you get glucose in, I don't know, if I were this intestinal cell, I'd be like, dude, I would like to eat that, please. And then, like, why would we ever send it into the blood? Let's just eat it. It's like being the ice cream man. If the ice cream, no, that's why I'm not the ice cream man. Because if I were the ice cream man, I'd eat all the ice cream. Like, here comes all the ice cream, and I'm supposed to sell it. Nice try, I'm going to eat it. Guess what? These cells do not eat. They can't eat glucose. So if I were going to be the ice cream man, I would need to, like, develop an ice cream allergy so that I couldn't eat ice cream, and that's the only way that I'd be willing to sell it. Because otherwise, I just would eat it all. Sounds really good, especially right now. So these cells can't eat the glucose, which means they're not going to try and keep it for themselves. They're like, dude, whatever. The only thing that they can eat is something called glutamine. That's how they get their energy. Awesome. So the fact that they can't eat it, we're going to build up a huge concentration of glucose in this cell. That's not the goal. What are you going to do about that? All we have to do is throw a glut into the mix. Remember the glut transporters? Glut transporters transport glucose down a concentration gradient. It'll go either way. Glut will move things into the cell if necessary or out of the cell if necessary. So in this case, the cell can't eat the glucose because it makes it sick, which means that, dude, you end up with tons of glucose. Let's go down the concentration gradient. Glut will allow that to happen, and guess where the glucose goes? Into the blood. So now you have glucose in the blood. What else did you get into the blood while you were at it? You also got sodium. You absorbed sodium from the lumen of the digestive tract as well. I didn't talk about this guy. What happens to the potassium? Your brain should probably be thinking, dude, if we built up too much potassium in here, that could stop the sodium-potassium pump. Like it can't push more. It's going to hit a limit for how much potassium can be inside this cell. And in fact, that's true. So usually these cells have potassium channels. The goal is not to create any kind of a membrane potential. We're not trying to do anything with potassium. We're just using potassium. Oh, I hope that doesn't make potassium feel bad. But we're just using it to get the sodium absorbed, and we'll just let the potassium back out again. No big deal. So as potassium concentrations increase in this cell, we're just going to let it back out through a potassium channel. Do you see how if I set up a small intestine cell with these transporters in this configuration, I can actually absorb glucose as long as I want? That's really important. In fact, we're going to come back to that and spend the whole last part of the lecture talking about how do we get the glucose into the rest of our cells. But before we do that, let's talk about protein absorption and how we go about that process.